Before we start, just a few pointers. Kim Livingston from our Mercer County Library IT department is here, and she's going to be here for the entire duration of the event. So if anyone is experiencing any kind of technical issues, please alert us through the chat window. If you could please also keep your audio muted to avoid audio feedback. The audio and video buttons are on the panel at the lower end of the screen. Professor Bhanot would like this discussion to be interactive. So when you have a question or comment, you can either type it out in the chat window, or if you prefer interacting directly, just alert me, again using the chat window, and I'll let Professor Bhanot know. You can then unmute yourself and join in. And now, Professor Bhanot, over to you.
Okay, thank you, Nita. And I hope this will be fun, because it's not worth it if it's not fun. So let me share my screen. I'm going to talk about Platonic solids, but let me again repeat what Nita said, that I'm a physicist. I'm used to my students telling me that whatever I'm saying is wrong. And so if you find whatever I'm saying is wrong or incomplete or something, and I can see that some of you who are here actually have the ability to correct me. I recognize some colleagues from various places I've been. So here we go. Let me share my screen. Okay, let me see now. First, I want to mute this. So I'm going to minimize this. I don't know how to minimize that. Is there a way to minimize this thing or not? Oh, yeah, okay.
What did you want to do?
I want to minimize this so it's in the corner somewhere. It doesn't bother me.
Minimize, you mean, so for all the participants, if you go to the top and just say hide everyone, then you will see the screen, the slides that Dr. Bhanot is showing. You will see them bigger on your screen. So if you want to do that.
Yeah. Okay, it looks fine. So let me start. So first of all, there is a small error in the title. This is not cool math you never learned in school. It's cool math that I never learned in school. And so it's possible that some of the stuff I say doesn't apply to you because you went to better schools than I did. If so, then please forgive me. But let me tell you why, what is cool about cool math. So first question is, what is cool math? So according to me, cool math is not school math. So for example, in school, you learn that the inside angles of a triangle sum to 180 degrees. But this is not true on the surface of a sphere. It's only true in planar geometry. And sometimes nobody tells you that. At least nobody told me that. Then you're told that there are things called prime numbers, which are special because their only factors are themselves and 1. But you're not told some other cool things about primes. For example, that the number of primes is infinite. Euclid proved this in 300 BC. That there is always a prime number between n and 2n for any n greater than 2, which was only proved in 1859. And that the number of primes less than some number n goes like n over log n, which was only proved in 1896. You also taught Pythagoras' theorem, as I was taught, but you're not told that it's only true in planar geometry. So cool math is all the stuff in red in this set of slides, and I never learned any of this stuff until I got older. So here's the cool math that I think kids should learn in school. First of all, you should be able to prove that the number of primes is infinite. This is a very beautiful and simple proof that I can show you. If you send me an email, I can send you a link to how to prove it. Prove that there are irrational numbers like square root of 2. An irrational number, remember, is a number that cannot be expressed as a ratio p over q, where p and q are relatively prime and q is not 0. You should be able to prove this theorem, which I call the little Goldbach theorem or the baby Goldbach theorem, which says that any odd number greater than 1 can be written as the difference of two perfect squares. It's actually quite trivial to prove, but it's kind of cool. You should be able to prove that there's only one prime triplet. A prime triplet is defined as a sequence of odd numbers. There's another triplet, of course, you will say 2, 3, and 5, but they're not separated by 2. So there's only one prime triplet. There's no more. Prove that the sum of the angles of a triangle on a sphere is greater than 180 degrees. This proof requires a little bit of thinking, but it can be done. And you should be able to prove that 6 colors are enough to color any planar map. If you persist and come to the next lecture, we will prove this using the theorem that I'm going to prove in this lecture. Okay, so if had I learned this in school, I would have become a mathematician, because this would have gotten me interested in even cooler math. Not saying that I'd be able to do anything with it, but there is cooler math. So cooler math is math that is easy to state but very hard to prove. So for example, here's a famous math problem that has never been proved. And that is the statement that there are an infinite number of twin primes. Twin primes are pairs of primes successive to each other, separated by 2 units, except for the first 2. People haven't been able to prove that they stop. People haven't been able to prove this at all. So if you prove this, you'll get a job in any math department anywhere in the world immediately, and many prizes too. Pi and E are irrational. That means they cannot be expressed as solutions to any algebraic equation with integer coefficients. This has, of course, been proved. Here's another one, which is easy to state. It says that any even number greater than 2 can be written as the sum of 2 primes. This is called Goldbach's conjecture, and it is unproven. Fermat's last theorem, which is that this equation x to the n, y to the n, plus y to the n equals z to the n, has no solutions for n greater than 2, which was recently proven by Professor Andrew Wiles when he was at Princeton, but now that he's at Oxford, he has been knighted by the Queen, and he is now Sir Andrew Wiles. And then there's the 4-color problem. That 4 colors are sufficient to color any planar map. There's a computer proof of that, and then subsequently there have been analytical proofs as well. So you asked me, what cool math are we going to do today? Okay, so what we're going to do is we will prove the second most beautiful theorem in mathematics, the second most, and then we will use it to prove that there are only 5 Platonic solids. So you will first immediately ask, well, what is the most beautiful equation? Forget the second one. So this is the most beautiful equation. E to the I pi plus 1 equals 0. And the person who discovered this equation or wrote it down first was Euler. Here, of course, you recognize all the ingredients. Pi is the ratio of the circumference of a circle to the diameter. E is the base of natural logarithms. I is the square root of -1. And the plus symbol we all know, and the 1, and the equal to, and the 0. So this is an amazing equation because it equates 2 transcendental numbers, E and pi, or 2 irrational numbers, an imaginary number I, and the numbers 1 and 0, which are familiar to us all. So this is supposed to be the most beautiful equation according to a consensus of mathematicians. So then the next question is, what is the second most beautiful equation? Well, the second most beautiful equation is something also that Euler discovered, which says the following. If you have any closed convex 3-dimensional shape made from polygons, such as the cube, for example, then there is a formula that connects the vertices, V, the faces F, and the edges E. V plus F minus E is always 2 for such a polygonal shape, closed polygonal shape. Are there any questions so far? Can everybody hear me? I guess, I hope. Okay, so all of this is the work of one amazing mathematician named Leonard Euler. He was born in Basel in 1707, and he died at the ripe old age of not very old, in the 70s. in St. Petersburg. He was one of the most prolific mathematicians ever. His collected works are in 92 volumes. After he became blind at the age of 59, he became even a better mathematician. And this is similar to many famous people. Many geniuses have this property. When you take away one of their faculties, their base knowledge or base abilities increase. So Beethoven, for example, became deaf. And after he went deaf, he wrote 5 sonatas, the Missa Solemnis, the 9th Symphony, and the last 5 string quartets. Same thing is also true of Milton, who became blind in 1652, after which he wrote Paradise Lost and Paradise Regained. Euler is the only mathematician to have 2 numbers named after him. The Euler number in calculus, E, the most basic number that everybody uses all the time. And there is another number called the Euler constant, gamma, which has not yet been proven to be irrational. E is known to be irrational. So let's go to the Platonic solids. What are the Platonic solids? Here they are. There are 5 of them: the tetrahedron, the cube, the octahedron, the icosahedron, and the dodecahedron. Okay, so these solids were known to the Greeks because the Greeks were obsessed with symmetry and beauty. Because they thought that nature follows some beautiful patterns, that if you discover these patterns, then you will understand nature. They knew that there were 5 perfect solids, and they called them the 5 Platonic solids. So what is the genesis of this name? Well, the ancient Greeks studied these extensively. For example, Pythagoras knew of 3 of them: tetrahedron, cube, and the dodecahedron. The octahedron and the icosahedron were discovered by a different person who was a contemporary of Plato. And Theodotus gave the first proof that there were only 5 solids. So if Pythagoras and Theodotus were the ones who discovered these Platonic solids, why are they called Platonic? You might wonder. Well, the reason is kind of funny. It's because Plato was the one who wrote about them. And the reason he wrote about them is he believed they represented the 5 elements. Earth was a cube, air was an octahedron, water was an icosahedron, fire was a tetrahedron, and heaven was a dodecahedron. So this should be a lesson to all you young people, that even if your theories are all nonsense, make sure they get published. Because if they get published, then you will be given credit for them in posterity. So Plato didn't know the first thing about mathematics, but they're still called Platonic solids because he was the one who made fuss about them. All right, so a more rigorous definition of Platonic solids. What is a Platonic solid? It's a convex shape, a curving in shape that can be embedded in a sphere. It is made out of regular polyhedra. All faces must be the same shape. All angles and edges must be equal. It has F faces, E edges, and V vertices, with the same number of faces meeting at each vertex. And here they are again, the 5 Platonic solids: the cube, the tetrahedron, the octahedron, the dodecahedron, and the icosahedron. Okay, so let's first see some properties of each of these. Here's the cube. It has 12 edges, 6 faces, 8 vertices. Let's count them. So here are the 4 edges on top, the 4 edges at the bottom, and the 4 edges around the sides. That's 12. And 6 faces up, down, left, right, front, and back. And 8 vertices, 4 and 4 on top. And notice something peculiar. V plus F minus E is 2. Tetrahedron. There's 6 edges, 4 faces, and 4 vertices. Again, V plus F minus E is 2. Octahedron. It's made from 8 equilateral triangles. E is 12 edges, 4 like this, 4 at the bottom, and 4 around, 8 faces, and 6 vertices. And V plus F minus E again is 2. Dodecahedron, a little harder to count because it's made from pentagons, but you can convince yourself that it has 30 edges, 12 faces, and 20 vertices. Again, V plus F minus E is 2. Icosahedron, E is 30, F is 20, V is 12. Again, it's a little bit tricky to count them, but you can do it. And V plus F minus E is 2. We'll actually prove that this V plus F minus E equals 2 is true not just for these solids, but for any solid made, which can be embedded in a sphere, which is made out of polyhedra. So there seems to be a definite pattern, but the question is, can we prove that V plus F minus E is 2 for any solid made from polygons? So I will illustrate the proof by using the cube. Okay, so we will pretend, we will consider the cube, but we'll pretend we don't know that V plus F minus E is 2 for it. A cube is a generic object for us, representing any convex polyhedra. So here's, take the cube. First thing I do is I remove one of the face on the top and throw it away. So obviously this decreases V plus F minus E by 1 because I've gotten rid of one F. Right? So whatever V plus F minus E was, now it's less by 1. So now let's squash the cube from the top, so it becomes two-dimensional. So then basically I'm going to take the top face which I removed and just push it down and extend the sides. Imagine it's made of, the sides are made of elastic. So this shows you, I've drawn the dots that show you which face goes where on the squashed cube. So the squashed cube is now in 2 dimensions, it's pushed in. Okay, so now you will notice that for the squashed cube, again, V plus F minus E is 1. Of course, we'll pretend we don't know that it's 1. But you can see it's decreased by 1. And that's because we removed the face. But let's pretend that we don't know what it should be, right? Okay, so now let's take this squashed cube and let's add an edge and a face. So we take one of these top faces and we add an edge. And now you will notice that by adding the edge, you have increased, by adding the edge, you have increased the number of edges by 1, and you've increased the number of faces by 1. So F and E are both increased by 1, and so V plus F minus E will not change by adding the edge. Okay, so we take this squashed cube with the edge added, and we add another edge and another face to somewhere in the middle. And again, you'll see that we added an edge, we added a face. V plus F minus E didn't change. We can keep doing this until all faces are triangles. And you can convince yourself that this will not change V plus F minus E. Whatever it was before, it will remain the same as it was before. Okay, so now once we are done making everything into triangles, we can start removing triangles. The first thing we do is we remove the outer triangles. So we remove an edge and we remove a face. And you can see that if you remove an edge and remove a face, that doesn't change V plus F minus E because you've removed a face and an edge, and that F minus E will remain the same. So now we can remove, if it's an outer triangle, we remove 2 edges, a face and a vertex. Again, we reduce V by 1, we reduce F by 1, and we reduce E by 2, so that now for the residual figure, V plus F minus E remains whatever it was before. We're pretending we don't know that it's 1. Okay, so we can keep going this way without changing V plus F minus E until all we have left is one triangle. And this is a bit of a leap of the imagination, but you can imagine it makes sense, right? You can keep removing stuff from here until in the end you'll be left with just one triangle. And for the one triangle, we know that V is 3, F is 1, and E is 3. So V plus F minus E is 1. That's the proof. And since the square was just a generic object, which was used as an example, this is true for all polyhedra. But let's recapitulate the proof so that you are convinced that it's true. So if you have any three-dimensional object made from polygons, you can remove one face and flatten it into 2D. You might have to stretch it a little bit, but that's okay. This decreases v plus f minus e by 1 because you've removed a face. Now we can add internal edges to make this object have only triangles without changing v plus f minus e. And now we remove the triangles one by one. Again, it doesn't change v plus f minus e until all that is left is one triangle. And for this triangle, v plus f minus e is 1, obviously. So it must have been 2 for the original 3D object. That's the proof. So we have now proven the second most beautiful theorem in mathematics. All right, so at this point, I will stop and ask if there are any questions, because now we're going to use this theorem to prove that there are only 5 perfect solids. Are there any questions?
When you remove the triangles, the ones that you removed only removed a face and 2 edges. Or, sorry. Sorry, I said that wrong. Go ahead.
Yeah, so I removed 2 kinds of triangles. One kind of triangle had I removed a face and an edge. And in another kind of triangle, I removed a face, a vertex, and 2 edges.
I see. Okay. So I missed the second type of triangle. That was my question. Okay. Thank you.
Yeah. Let me show you. It just takes a second. Yeah, here it is. So here, in this triangle, I removed 2 edges, the red ones, the red arrow, 1 face and 1 vertex.
Oh, right.
So if the triangle is sticking out, then that's what you have to do. If the triangle is not sticking out, then you remove 1 face and 1 edge.
Got you. Okay. Yes. Okay. Now I understand.
Okay. Any more questions? No?
Is there like a reason for the additional requirement of it having to be built inside of a sphere?
No, but it shouldn't. So it shouldn't have holes.
Okay.
If it has holes, then it's not 2 anymore. V plus f minus e. This is a formula without holes. It doesn't have to. It can have pointy things, but it cannot have holes.
Okay. So it has to be convex. Okay.
Yeah. So now let's take any polyhedron made from congruent polygons. Congruent polygons means that they are made from the same shape, right? The same size and shape. And here's this is a subtle slide. So let us say that m is the number of edges that meet in a vertex. So here's an example of a vertex with 3 edges. Okay. Then, now this is a crucial equation. If you multiply the number of vertices by m, you will get twice the number of edges. Why twice? Because every edge is shared by 2 vertices. So if you multiply m by the number of vertices, you're overcounting the edges by a factor of 2. Right? Everybody got that, hopefully? So now we can write v as 2e over m. Okay. And obviously m must be bigger than 3 because we are in 3 dimensions. We can't have a vertex in 3 dimensions with only 2 edges coming out of it, because then we would not be in 3D. Okay. So now let n be the number of edges per face. So here's a face with 3 edges. It's a triangle. Then if you multiply the number of faces by n, you get twice the number of edges, because each edge is shared by 2 faces. So multiplying the number of faces by n overcounts the edges by a factor of 2. You counted the edge twice for every face. So again, we can write f as 2e over n. And n again must be bigger than 3 because you can't make a face with less than 3 edges. It must be bigger than or equal to 3. Got it so far? So I'm going to replace f and v by these 2 numbers, n and m. So here's our original equation. V plus f minus e is 2. We saw that v was 2e over m, where m is some number bigger than 3 or equal to 3. And f is 2e over n, where n again is greater than or equal to 3. So I can substitute, if I substitute these equations into the formula, I get 2e over m from here. 2e over n for f, and the rest of it is the same. So I divide through by 2e, and I get this nice equation. 1 over m plus 1 over n minus half equals 1 over e. Since e is a positive number, this is greater than 0. And remember that m is greater than 3 and n is greater than 3. Okay, so this is our master equation, which we have to solve. Okay, so what does it mean to solve an equation like this? Because in algebra, you probably learned that when you have an equation with 3 unknowns, in this case m and an e, you need 3 equations to solve them. Or what we're going to try to do is to just work with one equation and find all possible solutions of this one equation. Okay, so let me write this equation down again. Here it is. And I know that m is greater than or equal to 3, n greater than or equal to 3, e greater than or equal to 0, greater than 0. So can we say something immediately about this equation? Anyone want to try to guess what we can say about this equation? How many solutions do you think this equation can have? Can it have an infinite number of solutions for m and n? Well, my claim is that this equation can have only a finite number of solutions. And the reason is that, first of all, m and n are greater than or equal to 3. So they have to be positive numbers. And if they're too large, then the left-hand side will become negative, and that doesn't make sense because the right-hand side is positive. So m and n are bounded. They can't be too large. Neither of them can be too, well, you'll see that they can't, neither of them can be too large. So now, let's now try to solve these equations. All right, so I wrote the equation out again. So I know that the smallest value of m is 3. So let's put m equals 3. If I put m equals 3 here, I get 1/3 here minus half. Well, 1/3 minus half is minus a 6th, and the 1 over n just carries over here. So you get this equation. 1 over n minus 1 over 6 equals 1 over e. And now you have to guess which values of n solve this equation. You can see that n has to be less than 6. So it can only be 3, 4, and 5. Otherwise, the left-hand side is negative, right? If n is bigger than 5, if n is 6, for example, the left-hand side is 0. So e is infinite. If n is greater than 6, then the left-hand side is negative. Okay, so let's put in n equals 3. So if n equals 3, then you get 1/3 minus a 6th, which gives you 1/6. So e is 6. And if you substitute e equals 6 in this equation above, you see that v is 12 over 3, that is 4, and f is 4. So you have something with 6 edges, 4 vertices, and 4 faces. Well, that's the tetrahedron. And remember that n and m are both 3. So every vertex has 3 things sticking out of it, and every face has 3 sides. Remember, n was the number of faces, number of edges to a face. Okay, so for n equals 3, we get a tetrahedron. For n equals 4, you substitute n equals 4. A quarter minus a 6th is a 12. And so e is 12. When you stick in e equals 12 here, you get v equals 8 and f equals 6, which is the cube. When you put in n equals 5, 1/5 minus 1/6 is 1/30th, so e is 30. E is 30, so v is 60 over 3, which is 20, and f is 12. Okay, 30 times 2, 60 over 5, which is 12. And that is the dodecahedron. Okay, moving right along. We can put m equals 4. If you substitute m equals 4, you get this equation. 1 over n minus 1 over 4 equals 1 over e. And now n can only be 3. Otherwise, the left-hand side is negative. So when n is 3 and m is 4, you get e equals 12. If you put 1/3 minus a 4th is a 12, so e is 12. If you substitute that into this equation, you get the octahedron. Finally, we can put m equals 5, and you get this equation. Now, of course, you would have guessed that n can only be 3 again. And this time you get the icosahedron. Now you might say, well, what about higher values of n? Can n be bigger than 5? Let's try. So let's put n equals 6. Then you get this equation. 1 over n minus 1 over 3 equals 1 over e. But we know that n has to be greater than or equal to 3. And e has to be finite. So this number n, there's no number n which satisfies this equation. This equation has no solution for n equals 3. So the solutions that we found are the only solutions of this equation. Even though it was a single equation in 3 unknowns, because of the conditions on these unknowns, we could show that it has only 5 solutions. And these are the 5 solutions, the 5 Platonic solids. So we have done something interesting, right? We have proven that there is this famous theorem of Euler's, the Euler characteristic, and that guarantees that there cannot be more than 5 Platonic solids or 5 solids made in a special way. That's it. Okay, so now, I mean, most people ask me a question at this point is, who cares about this? You know, what is the utility of this? And the reason I remember the utility of this is that when my kids were growing up, the teacher asked them this problem. It says you have, actually, they asked a different version of this problem, but I'm going to simplify it first. So suppose you have 2 homes and 3 utilities in a plane. And suppose you want to connect every home to every utility. How would you do it? And you want to do it in such a way that the pipes don't cross, because in 2 dimensions you can't have pipes that cross. Otherwise, there would be electricity flowing through water and gas flowing through electricity. So how would you do it? Well, you would do it. You would first connect the first home, and then you would connect the second home using these funny lines, right? You could avoid having crossing pipes that go from each home to each utility. But what if you have 3 homes and 3 utilities? So this was the problem that one of my kids got from her teacher, from his teacher, or I don't remember which kid, but one of them got this problem. And we spent a lot of time trying to work this through until we realized that it cannot be done. And the reason it cannot be done is because this is called a 3x3, K3x3 completely connected graph. And you can, so the problem is asking you, can you take this graph and move the red lines around in such a way that they don't intersect while keeping them in the plane? And you can show that you can't do that. And I will prove this in the next class using the Euler characteristic theorem that we proved. It's actually a very simple proof. And it goes by, I will give you a hint, it goes by assuming the opposite. Assume that it is possible to find a planar graph, and then we figure out what the properties of this planar graph must be, and then show that it can't be, it doesn't work. Okay, so these Platonic solids have another property which I will quickly talk about before I stop. It's something called duality. So imagine, put a dot at the center of each face of each Platonic solid and join the nearest dots to make an embedded polyhedron. So for example, here's the cube, and I have it embedded inside the cube, an octahedron, as you can see, by taking the face of each face of the cube, putting a dot on the face. So you have 6 dots, and then you connect the dots by triangles. Conversely, the octahedron can have an embedded cube inside. If you put a dot on the center of each face and connect the vertices so obtained. So the cube and the octahedron are dual pairs. The icosahedron and the dodecahedron are also dual pairs. And the tetrahedron is dual to itself. So duality is a beautiful property of many things. And duality is a symmetry property that is exploited a lot both in mathematics and in physics. I just wanted to give you a sense of this. And the reason I want you to think about duality is that there is a beautiful proof of Euler's formula on this website, which I encourage all of you to go to. If you just type 3 blue, 1 brown, on Google, you'll go to this website, which has a huge number of very cool math things and physics things. I have the proof embedded in here, but I'm not going to go through it because it takes a long time. But when I share the slides, you will have the proof. You can watch it, or you can just watch it on the website that I listed. Okay, so if you want to have even more fun, then of course, as I said, you should go to this website, which has really cool math. And there are the Riddler puzzles that come out every week, which I strongly recommend. And then I also recommend you buy and read many books about problem solving, fun problems. But this is the one that I really like. I got this as a Christmas present, and that was the best holiday season of after a long time for me. If you want to talk about this lecture or just want more suggestions for fun math books, you can email me. I'm always looking for a reason to do math as opposed to doing the work I'm supposed to be paid for. And now let me quickly introduce to you what's going to happen next week, if any of you show up. So the next week, I'm going to talk about graph theory and the birth of topology. And there's a story connected to this, that in the old Germany, there was a town called Regensburg, and in Regensburg there was an island connected to the mainland by 7 bridges, and you can see the 7 bridges here. It's hard to see, but you see 1, 2, 3, 4, 5, 6, and there's another one somewhere. Yeah, I think I missed the bridge here somewhere. Oh, here it is. 1, 2, 3, 4, 5, 6. There should be 7 anyway. And here they are. Yeah. So there are these 3 bridges. And the question that people in this town were asking was that, can I start from somewhere in the town, walk over all the bridges, so that I walk over all the bridges once, and I get back home after completing this walk? And people tried to do that by starting at different places, and they couldn't do it. And then somebody mentioned this to Euler as a problem, and Euler thought it was a stupid problem, not worth his time to spend any time on this, but he couldn't solve it. And so that irritated him so much that he finally decided that he's going to spend some time and try to figure this out. And the way he figured this out actually was by inventing something called graph theory. And so I will show you how graph theory led to topology, and how topology can be used to prove that the problem I showed you with the houses and the utilities has no solution, and how you can prove that 6 colors are sufficient to color any map using versions of the logic that Euler developed. So if you want to prepare for the next talk, I highly recommend this book, which is one of my favorite books on topology. Very simple. And I guess now I'm happy to answer any questions that you might have.
Gyan, why 6 rather than 4?
Oh, actually 4. Yeah, so it's actually 4, Cyrus, but the proof for 4 is highly non-trivial. The proof for 6 is very simple, so I can show it to you. The proof for 5 is a little less simple, but it's still doable. So if you insist, it's given in that book that I just showed you. The proof for 5 is shown here. The proof for 4 is a computer proof, the one that I know. And it's a bit of a pain to go through, because you have to go through classics. But maybe you and I can figure it out.
No. Okay, thanks.
Yeah. No, it's 4. The real problem is 4-color problem. But I'm only going to prove the 6-color version of the 4-color problem.
Okay.
Which is good enough for me.
Again, this is Dilip, very fascinating lecture. Actually, the duality thing I had not noticed earlier. I think that must be the reason the Greeks were so impressed. Symmetry is the core of all,
Exactly. Yeah, the Greeks love beauty and symmetry.
Yeah. The one question though, how does that Einstein E equal to mc square rank in terms of equation? Is it a physics? That's why it is excluded. I thought that is the most famous equation.
No, so mathematicians consider, okay, so mathematicians consider any equation with units to be non-interesting.
Oh,
So so when I listed the best, most beautiful, and second most beautiful, it's from a poll of mathematicians. If you ask physicists, you will not get these two equations. You'll get something more complicated like that, or you will get T mu nu equals G mu nu, or something like that. The equations that Einstein wrote down, or the equations of special.
I think that Heisenberg's equation is also, or inequality is also very, very philosophically interesting.
Yeah, there are many beautiful equations. So that's why, it's the thing is, what I find fascinating is that the way that you teach a kid something, I mean, convinces this kid to become somebody. And I think the way you teach math in school is not good, because what I learned I never learned any math in school. I learned math from my dad, who used to ask me problems that he didn't know the answer to. He told me, for example, that he showed me how to bisect an angle. And then he asked me, well, can you try to trisect an angle? And I tried and I couldn't do it. And then I asked him, well, how do you do it? And he said, I don't know. Nobody knows how to do that. So, then he told me that you can divide a circle into 5 parts, equal parts, using only a ruler and a protractor. And he showed me how to do it. And then he said that Gauss had proven in his PhD thesis that you could divide a circle into 17 parts. And I asked him whether he knew the proof. And he said he didn't understand the proof. And it's only recently that I discovered the proof. And the proof is not that difficult, but my dad didn't know it. So I think telling kids facts doesn't help them so much as firing their imagination with ideas. And I would have become a mathematician had I not become fascinated with physics. Maybe I would have not done as well. I mean, I'm not sure what I did in physics was any good either. But in math is harder because it's purer. But to answer your question, Dilip, because E and M and C all have units, mathematicians don't consider this a relevant equation.
On the other context, this notion that there are 5 elements, it is interesting to Hindu religions also. So is there any non-geometrical imperatives that makes this 5 element to be important universally?
I don't know. You should. So there is a book written by a friend of mine who used to be in Cyrus's university, Hassan Padamzi. So Hassan wrote this book, and he has a series of lectures as well. It's called The Physics of Heaven and Earth.
Yeah.
And in this book, he explores all these ideas. How did the ancients come to realize that nature, that there's symmetry in nature and there's beauty and symmetry in nature? The business with proof of things, it's a relatively recent concept. For example, Aristotle used to believe that women have fewer teeth than men, which is patently wrong, because he could just have counted the teeth in people's mouths, and he would have convinced himself that it's not true. They have the same number of teeth. But nobody tried to prove things. People just had a philosophy. And if it was beautiful, and if it looked elegant, and if you were famous enough, then it was true. He believed that falling objects, heavier objects, fall faster. And it was just wrong. But he never did an experiment to prove it. So there's a lot of mythology that tries to make sense of nature and beauty and complexity and things like this. But I think without rigor, all of that is just philosophy. That's why I had this last slide where I showed you. Right? So on the left is sociologists, and the psychologist says sociology is just applied psychology. And the biologist said psychology is just applied biology, and so on and on and on, until the physicist says chemistry is just applied physics. But the mathematician, which is way out on the right, says, hey, you guys, I can't see you from way all over here, because I'm so far away from you. I'm so totally pure. So the good thing about math, which I really think is something we should all consider, is that once you prove a theorem, there is no way it can be false. Newton wrote down his famous laws, and for a long time they were true. But then along came Einstein, and suddenly Newton's laws are an approximation to Einstein's laws. And once we find more subtle laws, if the string theories succeed, and find more subtle laws about how the forces of nature work, then maybe Einstein's theory will have to be revised as well. Quantum mechanics, for sure, needs to be revised at some point when we reach the scale of strings. So, but mathematical theorems are true. Once you prove them, they're true forever. And so that's the purest set of theorems.
So Gyan,
There are some more questions here. One is from Soren Alexei. Can we prove Euler's theorem without equations?
Whose theorem?
Euler's formula.
Sorry, I don't know the proof. If you know the proof, please tell me. Is there a symmetry proof you need?
Soren, would you like to join in?
Yeah, I don't know the proof.
I don't know either, but there are a couple of things coming from geometry that could definitely make the proof easier. And I was thinking that would be fun. I mean, the Greeks did it without equations. Equations came later from Arabs.
Yeah, so I don't know the Greek proof. It would be nice to know the Greek proof. You're right.
Yeah.
I will look for it. Good question.
I will think about it. We'll send you an email.
Yeah, let me know if you come across a solution. It would be very cool.
So
okay, we have one more question from Seon. Would you like to voice your question, please?
Sure. Yeah. No. I was. Your talk made me think of something I feel like I've read before around mathematicians being hired by, I think it was a phone company or something like that, to minimize or find the most efficient solution for connecting cell towers together or something like that. I feel like I've seen this invoked as an example of how to most efficiently lay out a grid of cell towers or something. Was it Feynman or I don't know, maybe it was Erdős? Someone was asked to do this.
Yeah, so these kinds of questions appear a lot. Graph theory appears a lot in circuit design, for example, and in laying out memory close to CPUs on a board. So because you want the numbers to reach the CPU at some rate which is fast enough, so that you don't just wait for the data to arrive. So computer scientists who design architectures use these concepts a lot.
Can I add to this question just by saying that is there something about this that is more efficient, or like that somehow ties to optimization or efficiency, or is that just like in terms of shortening distances, or like why would that seems like a natural application, but I'm not sure if I'm misreading the characteristics of this solution.
No, I don't know. You may be right. I mean, but so if you are, let's say you are moving along the surface of a sphere, is this the shortest way somehow to move around if you are allowed?
Right.
I don't know. It could be. Yeah, I have to think about it. But you have to specify the problem. Right? So you have to ask me the problem. I mean, there are many famous problems of minimizing the distance. Like you have a cube, you have an ant sitting on one corner, and there's food on the other corner, on the opposite corner. What is the shortest path for the ant to walk to get from one place to the other, and how do you find it?
Right.
And the solution is very simple, right? What you do is you remove a face, you flatten then make a line, and that line, whatever that line traces on the surface of the cube, is the shortest path. And it's not the obvious one. It's not along the edges, or it's not along the diagonal at all.
Right. That one I know, but.
Yeah. So,
this certainly, I would have to specify a question, but this triggered that thought in me. I thought maybe you might have remembered the story.
No, I don't. No, that's a good question again. This is just a small theorem, isn't it? Huge theorem. I don't
right.
know.
Yeah.
Any more? Dilip had another question.
Yeah, I have a question that the Egyptians, at the time of pyramid, did they know all the 5 Platonic structures, or they had only a few of them?
Well, yeah, so good question. I don't know, because, you know, the Greeks wrote a lot of their stuff down, and the Egyptians did not. A lot of, so, you know, the hieroglyphs were only deciphered recently, and all that's left of what the Greeks knew or didn't know is in the records of merchants. And so mostly we know they knew how to add and subtract, and they knew how to keep Excel sheets like things where they made sure that they paid for them. But we don't really know their mathematics. In fact, a lot of the mathematics of the
Yeah.
This fidelity bill needs some attention.
Sorry, Cyrus, you were saying something? So a lot of the mathematics that we now take for granted actually was not invented by the West. For example, you know, the word algorithm comes from a guy, an Arabic mathematician named Al-Khwarizmi, and he also invented the word algebra, which most people don't realize, because he wrote a treatise on algebra and proofs, algorithmic proofs, that was discovered by the Crusaders, who brought it to Europe, and all of a sudden, you know, Arabic math was famous because it was easy to do, and you know, it was very well thought through. But a lot of the history of the inventions in the Middle East and the Far East are not known. Even in Indian math is not very well known because there's not good records of any of this stuff. I mean, we don't even know about the kings before you know, 200, 300 BC. Whereas in the West, there was a written. The Greeks kept a good record. So a lot of the math that was invented by the Egyptians and the Arabs is unknown to us, and disappeared over time when Islam came and took over everything.
Any more questions?
Well, the real test will be how many of you will come back next week, if any. We will see.
Okay, so thank you, Professor Bhanot, for this really fascinating presentation. If anyone is interested in getting the slides from today's presentation, please just email me and I'll send them to you. Thank you everyone for participating. We look forward to having you all back next Monday, August 31st at 7 p.m. for part 2 of the Cool Math program.
Thank
Good
you,
night.
everybody. Bye.
Thanks.
Bye-bye.